Okay, so we will start with the derivation, that is, derive an expression for electric field at any point near the surface of a uniformly charged infinite plane sheet using Gauss law. Okay, okay, fine. Now coming to this, so as you know that we need to find the electric field at any point near the surface of a uniformly charged infinite plane sheet. Consider that you have a sheet, okay, where the positive charges are uniformly distributed over it. Okay, so the thickness of that thin the thickness of the sheet is very thin. Okay, I mean very small. So as you know that, let us consider a point P, okay, to find the electric field. Let us consider a point P where the electric field has to be calculated, okay, on both the sides of the sheets. Okay, so at that point you know that in order to calculate the electric field at point P on the both the sides of the sheet, so what we are going to do is we are going to consider a cylindrical Gaussian surface. Okay, we are going to consider a cylindrical Gaussian surface. Okay, so where you are going to calculate the electric field at the point P. So you can see the figure. Okay, how we have considered that a cylindrical Gaussian surface in order to calculate the electric field. Okay, in order to calculate that we have to consider that. So now you need to um, find the direction of electric field. So as you know that since we have considered the positive charge to be uniformly distributed over the surface, so hence what happens, the electric field will be directed towards the right. Okay, electric field will be directed towards the right. So now when you consider the area vector, okay, so let me consider uh, a small area here itself where you have considered the point P. So what happens, the electric field will be directed towards the right. Similarly the area vector direction will also be directed towards the right side itself. Okay, similarly even here at this point also, if you consider even this is a point where you need to calculate the electric field. So as you know that even the electric field direction will be towards the left, and even the area vector direction will be directed towards the left. Okay, so as we have considered in the last class itself, I mean when we went through about the derivation of electric field due to an infinite long charged wire. Okay, so we have divided the cylindrical surface, Gaussian surface, into three parts, right? In the same way we are going to divide the cylindrical Gaussian surface into three parts. This is the first part, this is the second part. Okay, so the end parts, so this is the first part, this is the second part, and this curved part, okay, will be a third part. Okay, that curved surface will be a third part. So now we will consider the curved part. So as you know that the electric will be directed towards the right, whereas the area vector will be directed towards the upward. Okay, so now in order to calculate the total electric field, okay, through the Gaussian surface, so what happens, the electric flux through, so the electric flux through both the sides, okay, that is the ends of contributes to the electric flux. Okay, whereas the curved surface doesn't contribute to the electric flux because the angle between the electric field and the area vector comes out to be 90 degree. Okay, so hence cos 90 is 0, so we are going to neglect that. Okay, I mean we will leave that. So now next is nothing but, as you know that the total electric flux is phi 2. Okay, so we will consider this as a curved surface as part 1. Okay, and this both the ends as part 2 and part 3. Okay, so now as you know that in order to calculate the total electric flux, so at the second part the electric flux comes out to be as Ea, and at the third part also the electric flux comes out to be as Ea. Okay, so hence the total flux through the Gaussian surface comes out to be as phi is equal to phi 1 plus phi 2 plus phi 3. Okay, substituting that, phi 1 value is 0, phi 2 and phi 3 value is Ea plus Ea, that comes out to be 2 Ea. Okay, so the next is the total charge enclosed by the Gaussian surface. Okay, so since it is a sheet, right, so we are going to make use of this surface charge density. Okay, what is surface charge density? Charge per unit area. Okay, so sigma denotes the surface charge density. Sigma is equal to q by a, right? So hence the value of q comes out to be, if you take out that q on the right hand side, the value of q comes out to be as q into a. Okay, so hence q is equal to sigma into a. So now what we are going to do is, as you know that according to Gauss law, the Gauss law equation is phi is equal to q by epsilon naught. Okay, so when you compare, I mean, you're substituting the value of q, you are going to get the value of phi as phi is equal to sigma a divided by epsilon naught. So now consider this as equation 1 and this as equation 2. When you compare equation 1 and 2, the LHS are same. So comparing the equations, you can write 2EA is equal to 1 by epsilon naught into sigma into A. Okay, so hence A and A get cancelled out. The left out thing is nothing but E is equal to sigma divided by 2 epsilon naught. Okay, so this is regarding the derivation of electric field at any point near the surface of a uniformly charged infinite plane sheet. Okay, do one thing, just go through this derivation. Okay, even this is an important question which we ask for 5 marks, but they have given here for 3 marks. Okay, so there is a chances of asking this derivation even for 5 marks also. Okay, so go through the explanation, figure, mathematical part. In case if you have any doubts, you can ask me. Okay, just go through for a few minutes. Students, any doubts regarding this derivation? Okay, fine. So with this, we have completed the revision of the chapter electric charges and field. Okay. So now coming to the third, I mean the second chapter, that is potential, electric potential and capacitance. Okay. We will start with that. Okay, see you. The 13th question is of the chapter, second chapter. Okay, second, I mean 13th question is of second chapter. So we'll start with that. So the question is, what are equipotential surfaces? Write the properties of equipotential surfaces. Okay, what is an equipotential surface? It is a surface where at every point of which the electric potential is same or constant, where the value of electric potential remains the same. Okay, so that type of surface is called as the equipotential surface. Okay, so next coming to the properties of equipotential surface, that is nothing but the first one is the work done in the work is done in moving a test charge from one point to another on an equipotential surface is zero. So as you know that when you move a charge from one point to another point in the equipotential surface, so the work done comes out to be zero. Why is that? Because as you know that work done is equal to V into Q. Okay, since the V remains the same. Okay, so what happens, the value of V comes out to be zero there. Anything multiplied with zero is zero, so the work done comes out to be zero. Okay, so the second property is, for any charge configuration, equipotential surface through a point is normal to the electric field. As you know that always the electric field lines will be perpendicular to the surface. Okay, so when you take a equipotential surface, the electric field will be normal to it. Okay, so next in two equipotential surface will never intersect. Okay, why do they never intersect? Because at the point of intersection, if the two equipotential surface intersect, so at the point of intersection there should be a two values. Okay, so hence which is not possible. Okay, at any point. Okay, whichever the point you consider, so at that point there should be any one value. It cannot be two value at the same time. Okay, so hence we say that two equipotential surfaces never intersect. Okay, so the next is the important derivation, that is derive the relation between the electric field and potential for a point charge. Okay, so even this is a 3 mark question. So as you know that what we are going to do is we will consider a point charge q which is situated at O. Okay, so next what we are going to do is we will consider 2 points which are very closely spaced. Okay, and we are going to consider, let V be the potential at A and the potential at B be V minus dV. Okay, so next just when you see the figure you will come to know. Okay, so next is nothing but dr is the, okay, so dr is nothing but the distance from the point, distance dr is the distance of the point A from B. Okay, so the distance between A and B is dr. So now what we need to do is we need to move a positive charge from B to A against the electric field of charge q. As you know that since we have taken a charge of I mean positive charge we have taken, that is plus q, since you know that even a test charge is a positive charge, so when you make this test charge to move towards the, there is a source charge, that is plus q. So what happens, the test charge will be repelled. Okay, so in order to overcome that electrostatic force of repulsion, what we need to do is we need to do some work to move the unit charge towards the source charge. Okay, so the work done is expressed as dw. Okay, dw is equal to vector e dot vector dr. Okay, as you know that we have come across this relation, that is the dw is equal to vector e dot vector dr. Okay, that is nothing but equal to, that is expressed as e dr cos 180 degree. Why is that 180 degree? As you know that the electric field is directed towards the right. Okay, the electric field is directed towards the right, and we are moving the unit test charge towards the left, so the angle is 180 degree. Okay, so hence cos 180 is minus, so that comes out to be as minus edr, which is equation 1. Okay, so next, this work is equal to the potential difference, that is dw is equal to va minus vb. Exactly. Okay, whatever the work you are going to do, that itself is the potential difference between the point a and b. So that is expressed as dw is equal to va minus vb, which is taken as equation 2. Okay, so compare equation 1 and 2. So when you compare equation 1 and 2, LHS are same, so hence you can write minus EDR is equal to VA minus VB. Okay, so next is nothing but minus EDR is equal to, we have just substituted the value, the VA value is V and VB value is V minus DV. Okay, so you can see here, that is what we have taken here. Okay, V and V minus dV are the potential at point A and B, right? So hence replacing that, you can see there V and V get cancelled out, so we are left out with dV. Okay, so hence you can write that one as E is equal to minus dV divided by dr. Okay, so hence it is concluded that the electric field at a point is the negative gradient of potential at that point. Okay, so this is regarding the relation between this electric field and electric potential, which is very important, which will be asked for 3 marks. Okay, just go through about the question 13 and 14 once. In case if you have any doubts, you can ask. Just go through. Any doubt, students? Okay, fine. We will move to the next question, that is 15th. Obtain the expression for potential energy of a system of two charges in the absence of external field. Okay, even there is a expected question in your examination. You need to find the potential energy of a system of two charge in the absence of electric field. Okay, so as you know that it has been given, consider 2 point charges q1 and q2 with position vectors vector r1 and r2. Okay, so let us consider a point A, okay, where you need to bring the charge from infinity to a given point, that is at point A. Okay, let us say that now we are bringing a charge q1 from infinity to point A. Okay, so what is the work done? So work done comes out to be 0 because there is no charge present before bringing the charge q1, right? So hence there is no work done, so hence work done comes out to be 0, that is w1 is equal to 0. Next, since you know that, let us consider another point B. Okay, so now this is the point A where we have brought the charge q1, okay, from infinity to point A. So now let us consider the point B. Okay, let us consider the point B. Okay, so now what we are going to do is we need to bring the charge q2 from infinity to point B. Okay, so now let us say that the potential at point B due to the charge which is present at point AB, V is equal to 1 by 4 pi epsilon naught into q1 divided by r. Okay, so now next is nothing but we need to bring the second charge. So let us say that we have brought the charge from infinity to uh, point B. We have brought the charge q2. So now what is the work done? Obviously the work done will be w2 is equal to vq2. Okay, So which is taken as next, if you substitute the value of V, so that comes out to be as W2 is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R12, okay, where R12 is the distance between the Q1 and Q2, okay. So this R what we have taken, that itself you can consider that one as R12, okay. R12 is the distance between A and B. So hence the equation 3 comes out to be as W2 is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R12, okay. So next, the total work done comes out to be adding W1 and W2. So hence W is equal to W1 plus W2, that is nothing but equal to, obviously W1 is equal to 0, and the W2 values if you substitute, that comes out to be 1 by 4 pi epsilon naught into Q1 Q2 divided by R12, okay. So hence whatever the work done you are doing, okay, that itself will be stored, that work done itself will be stored in the form of potential energy, okay. So hence it is said that the electric potential energy of 2 point charges is the work done in bringing each charge from the infinite distance to their location, okay. That whatever the work you are doing to bring the charge from infinity to a given point, that itself will be stored in the form of potential energy. So hence the W is replaced by U there, okay. So hence the final equation is expressed as U is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R12, okay. So this is regarding the expression for potential energy of a system of two charges in the absence of external electric field, okay. Just go through once.